A computer chip modeled after the human brain just solved physics equations that normally require a room-sized supercomputer burning through megawatts of power, and it did it using a fraction of the energy. That study dropped today in Nature Machine Intelligence, and Maya, this one kind of broke my brain a little bit.
Okay, I love the irony of that. Your brain broke thinking about brain-shaped computers. But seriously, this is a huge deal. Researchers at Sandia National Laboratories, which is a Department of Energy lab, they built an algorithm that lets neuromorphic hardware solve partial differential equations, PDEs, and if you don't know what those are, don't worry, we're going to break it down.
So, let's start with the basics. What is neuromorphic computing? The word literally means shaped like the brain. These are computer chips that are designed from the ground up to mimic how biological neurons work. Instead of the traditional approach where you have a processor over here and memory over there and data shuttling back and forth between them, neuromorphic chips integrate everything together just like neurons do.
Right, and the key difference is how they communicate. Traditional computers use continuous streams of data. Neuromorphic chips use spikes. Little bursts of electrical signals just like real neurons firing in your brain. And here's the wild part. They only consume power when a spike happens. If nothing's firing, the chip is basically asleep. That's why people get so excited about energy efficiency.
And to put that energy thing in perspective, your brain runs on about 20 watts. That's less than most light bulbs. Meanwhile, a modern supercomputer like the ones used for nuclear weapon simulations can consume 20 megawatts or more. That's a million to one ratio. The brain is doing insanely complex things, like catching a baseball or recognizing a face in a crowd, on the power budget of a dim light bulb.
Which is the exact point that Brad Amoni, one of the lead researchers, made. He said, and I love this quote, pick any sort of motor control task like hitting a tennis ball or swinging a bat at a baseball. These are very sophisticated computations. They are exascale level problems that our brains are capable of doing very cheaply.
Exascale level for context, we only just built the first exascale supercomputer a few years ago. Frontier at Oak Ridge National Lab, it cost hundreds of millions of dollars, and Amon is saying, your brain does comparable math every time you catch a set of keys someone throws at you.
So the big question has always been, okay, these brain-like chips are cool for pattern recognition, image classification, that sort of thing, but can they do real math? Can they solve the hard equations that physicists and engineers actually need? And until now, the answer was basically, we don't think so.
Right? And that's what makes this Sandia study such a bombshell. They proved that neuromorphic hardware can solve partial differential equations. Let me explain what those are because they sound scary, but the concept is actually pretty intuitive.
A partial differential equation is basically a mathematical recipe for how something changes across space and time. When meteorologists forecast the weather, they're solving PDEs. When engineers figure out if a bridge can handle wind loads, PDEs. When physicists model how heat moves through a nuclear reactor, PDEs. They are everywhere in science and engineering.
And they're notoriously hard to solve. You can't just plug in numbers and get an answer. You have to break the problem into millions or billions of tiny pieces and crunch through all of them. That's why we build supercomputers. That's why the Department of Energy spends billions on computing infrastructure. PDEs are the bread and butter of scientific simulation.
So what Thielman and Amon did is they created a new algorithm that maps PDEs onto neuromorphic hardware. And the key insight is that their algorithm is based on a well-known model from computational neuroscience. A model of how cortical networks in the brain actually work. They showed that this brain model has a natural, but in their words, non-obvious connection to partial differential equations.
That's the part that gives me chills. This model of brain circuits has been around for 12 years, and nobody realized it had this deep mathematical connection to PDEs until now. It's like discovering that a painting you've had on your wall for a decade has a hidden message in it.
And it works. They ran it on neuromorphic hardware and it solved real physics problems. The paper is in Nature Machine Intelligence, which is one of the top journals in the field. This isn't speculation, this is peer-reviewed results.
Now let's zoom out and talk about the landscape, because Sandia isn't the only player here. There's a whole ecosystem of neuromorphic chips being developed. Let's run through the big ones.
The one that kind of started the modern wave is IBM's True North, which came out in 2014. It packed a million neurons and 256 million synapses onto a single chip, and it ran on just 70 milliwatts. For comparison, the processor in your phone uses several watts. True North was a proof of concept that you could build brain-scale computing on silicon.
Then Intel jumped in with Loihi and then Loihi 2. The second generation chip supports up to a million neurons and 120 million synapses per chip. But here's where it gets really interesting. In 2024, Intel built HalaPoint, which is the world's largest neuromorphic system. They crammed 1,152 Loihi 2 processors into a chassis the size of a microwave oven.
A microwave oven. And this thing has 1.15 billion neurons and 128 billion synapses spread across over 140,000 neuromorphic processing cores. The entire system consumes 2,600 watts. Compare that to a traditional supercomputer that fills a warehouse and drinks megawatts.
And then there's brain scales out of Europe, from Heidelberg University. Their approach is different because they use analog circuits instead of digital ones. The neurons on brain scales are physical analog circuits that operate 1,000 times faster than biological neurons. It's like they took the brain metaphor and said, what if we made it even faster?
Each of these platforms has its own philosophy. True North was about massive parallelism at ultra-low power. Loihi is about programmability and flexibility. You can actually write custom neuron models. Brainscales is about raw speed through analog computation. They're all different bets on how to build the brain in silicon.
So now let's connect it back to the Sandia breakthrough. Why does this matter beyond just being a cool science result? The answer comes down to two words: energy and security.
The Department of Energy and the National Nuclear Security Administration, NNSA, they are the ones funding this work, and for good reason. The supercomputers that simulate nuclear weapons physics consume enormous amounts of electricity. If you could do the same simulations on neuromorphic hardware at a fraction of the power cost, that's a game changer for national security.
And it's not just about saving on the electric bill, although that matters too. It's about what becomes possible. If you can run physics simulations that are 100 or 1,000 times more energy efficient, you can run more of them. You can simulate more scenarios, you can iterate faster. In fields like climate modeling, material science, drug discovery, the bottleneck is often just raw compute power and the energy to run it.
Amoni put it really well. He said, you can solve real physics problems with brain-like computation. That's something you wouldn't expect because people's intuition goes the opposite way. And in fact, that intuition is often wrong.
I love that. We built these massive traditional supercomputers to solve physics, and it turns out the 3-pound computer sitting in our skulls has been solving physics all along. We just didn't realize it.
And there's another angle here that I think is genuinely profound. This research doesn't just help engineering. It might help us understand the brain itself. Thielman said that they base their algorithm on a well-known cortical circuit model, and by showing it can solve PDEs, they've revealed something new about what that brain circuit might actually be doing.
Think about that. By building computers that look like brains, we might learn what brains are actually computing. Imon even suggested that diseases of the brain could be diseases of computation. If we understood what computations the brain is performing, we might understand what goes wrong in conditions like Alzheimer's or Parkinson's.
That's the thing about neuromorphic computing that makes it different from just another hardware trend. It sits at this incredible intersection of computer science, physics, and neuroscience. Every advance pushes all three fields forward.
So where does this go from here? Thielman asked a really provocative question. He said, if we've already shown that we can import this relatively basic but fundamental applied math algorithm into neuromorphic, is there a corresponding neuromorphic formulation for even more advanced applied math techniques?
In other words, PDEs are just the beginning. There's a whole universe of mathematical tools that scientists use: finite element methods, spectral methods, Monte Carlo simulations. If those can also be mapped onto brain-like hardware, we're looking at a fundamental shift in how scientific computing works.
And the Sandia team is explicitly talking about building neuromorphic supercomputers, not just chips, not just research prototypes, full-scale supercomputers based on brain-inspired architecture. That's the vision.
We're watching the early days of something that could reshape computing as much as the transistor did. The brain has been the most efficient computer in the known universe for millions of years. We're finally starting to steal its secrets.
And apparently, one of those secrets is that it's been doing calculus this whole time. Your brain right now is solving partial differential equations just to keep you balanced in your chair. Think about that.
I will never look at my brain the same way again.
That's episode 60 of Things I Know Nothing About. If this blew your mind, hit subscribe, share it with someone who needs to hear this, and we'll catch you next time.
Stay curious, everyone.